In this section, we're going to have a look at the differences between the electricity provided by a cell or a battery and the electricity provided through the mains plug sockets that we have around the room. So come on in closer and let's take a look at this battery. So what have we got set up here? Well, we've got a cell and we've got multiple cells forming a battery just here. And we've also got an oscilloscope. And this oscilloscope is going to tell us the amount of potential difference between these two wires. At the moment, the two wires are connected together with nothing in between. And so it's showing the trace across here of 0 volts. When I plug this in to one of the cells, that we can see that this line has moved. It's now detecting 1.5 volts. If I move this across 2 cells, you can now see that it's at 3 volts. How high the line is on this screen indicates the amount of potential difference between these two wires. Here we have a battery. This end of the battery is 12 volts. And this end of the battery is 0 volts. And I've connected this end of the battery to this large metal plate. And this metal plate has a huge number of electrons, so that if there's any possibility that this is not 0 volts, and this certainly will be, it is an earth. And we're putting it in the circuit to demonstrate one particular thing. That this end is most definitely 0 volts. And this end is 12 volts. So what I've got here is I've got a resistor, and at the moment, though there is a potential difference across it, there is no current flowing through it. What I know is that with a single resistor in the circuit, 12 volts of potential difference provided by the battery is going to be equal to the 12 volts of potential difference that are used overcoming the resistance of that resistor. Now in the dark, so that you can see, I've got this wire. And if I connect this wire to the resistor on the terminal after the at the end of the resistor, you can see that there is absolutely no sparking at all, because this end of the resistor is now at 0 volts, the same voltage as this metal plate. And so therefore we know that this wire and everything this side is at 0 volts. But it's not the same on the other side. Before we go into the resistor, we are at 12 volts, the same as this. And so what we see is sparking. So in this circuit, everything upstream of the resistor is like a live wire, and everything downstream of the resistor is like a neutral wire. Now these words aren't normally used in situations of direct current, but they are going to become useful when we start talking about alternating current. Now I have a power supply plugged in to my oscilloscope. I've got the wires going into the DC, the direct current part of this power supply. You can see on the screen that it's reading a voltage of about 6 volts. Now what I can do with my power supply is change the amount of voltage. You can see what I can do is I can turn it up and I can turn it down. Now this here I can alternate and make move up and down. Now this of course is quite crude because I'm doing it with my hand. But what you can see at times we have got a very large voltage in the live wire compared to the neutral wire. So just as before, when there is a large voltage through the live wire, we actually see that we have a very high voltage on here. But that the live wire always is the one that carries the potential difference, with the neutral wire, the other wire, remaining at 0. It is the difference between the two that would create, in this case, an alternating current if it was connected to a circuit. Now look at this. Rather than me turn this up and down, what I've got here is a little windy handle. And it's going to now enable me to change the voltage of the live wire up and down relative to the zero voltage of the neutral wire. And on the screen, as I wind this around like this, you can see that I am getting the voltage both positive and negative at various different points in the cycle. I could increase the frequency by rotating it even faster. I could take it up and up and up and up until eventually I was producing something similar to the electricity that is coming through the main supply. Now, one more thing. You can see the frequency, how many oscillations I get per second, appears on this screen with the separation of those peaks, with a high frequency putting the peaks together and a low frequency separating those peaks out. You can also see that the amount of voltage, or the potential difference, is the Y scale. So how high these peaks are speaks about just how much voltage I was going to get. A major difference between the 12 volts of DC provided by this and the 230 volts that comes through mains electricity would put the mains electricity on a scale that would be too big to see, and so we would have to rescale it on the oscilloscope. So now look here. I've got a Westminster power supply here, and I'm going to show the trace on the oscilloscope that is produced by an alternating current. Now, a key thing here is we're not plugging the 230 volts mains electricity straight into the oscilloscope because it would be dangerous. So we're using this Westminster power supply has a small transformer in it which actually lowers the voltage. So technically it will not be 230 volts on here, but it makes it slightly safer for us to investigate. We have an alternating potential difference between these two yellow terminals here. What we can see when we switch it on is we have an alternating potential difference on the oscilloscope. So what is going on? Well, an important thing is to keep that distinction between the neutral wire and the live wire. Like before, the neutral wire is always at 0 volts, whereas the live wire is at one moment at positive 230 volts and at another moment negative 230 volts. And so it's continually switching direction. Now this means that if we plugged it into a circuit, we would see an alternating current. It also means that the live wire is very dangerous indeed. That if we were to connect ourselves to the live wire, the very large potential difference between it and me would result in an electric spark or a shock, whereas the neutral wire is always 0. And so I shouldn't be shocked at all because we're at the same voltage. Sometimes in domestic situations, the circuits are incorrectly constructed. And so the neutral wire may in fact be dangerous in those situations. So it's better to be safe than sorry and not do anything unless you know what you're doing. Now, some people have a lot of trouble with alternating voltage and how it creates the current that also alternates. So here is a nice conceptual model which hopefully will help you understand it. What we have here represented is the neutral wire, and at the other end of this string we have the live wire. And what happens is the live wire, though it doesn't physically move, it changes from having a high voltage to 0 voltage to a high negative voltage and back again. And so the voltage in the live wire changes from a very high positive value to a very high negative value. What happens when it changes is it causes the current to flow in a different direction in the wire. So if we take the live wire now and we put it down there then the current has now moved down in that direction. A split second later, 0.01 seconds, and the current has come back the other way. And so what happens over the complete cycle is the current flows one way and the current flows back again. Now there's a number of tiny little nuanced details that make this model so good. First of all, you can see that the neutral wire always stays at 0 volts. So if I accidentally touched this, it shouldn't cause me any harm. But the live wire it continuously moves between high voltages, and so touching that wire would give me harm. Now here's another subtle detail as well. Notice how the current flows away when the voltage is very positive, and this is more to do with historical reasons. The direction of conventional current was made on the presumption that the charges were positively charged. And so going from a region that is positive voltage is like equivalent to a positive charge, and the conventional current was drawn going the other way towards the negative charge, or the more negative voltage. And so this is really quite accurate, that the current moves toward the more negative voltage and away from the more positive voltage. So that's a subtle detail, it's not anything that you need to particularly understand, but it is a subtle detail. A second thing to understand is that actually the voltage goes as high as 325, but it doesn't actually stay very long at that value. In fact, it spends, if you think about going between the 0 point up to 325 and back again, the kind of average value that it has over that time interval is 230. So when we talk about the voltage of mains electricity, we're not talking about its maximum voltage, but instead we're talking about its average voltage over the course of half a cycle. So an alternating potential difference going to a very high positive value and then down to a negative value of the same magnitude again and again and again is in a circuit loop going to create an alternating current. Now here we have got a signal generator connected to a pair of LEDs, and these LEDs with a resistor. LEDs only allow electricity to flow through them one way. So why are they alternatively flashing? Well, when the alternating potential difference is positive, it's creating a current that will only flow through the red one. When the alternating potential difference is negative, it is creating a current that will only flow through the green one. And you can see these are flashing about twice every single second. So this would have a frequency of about 2 Hertz. Now, this is not the frequency of mains electricity. Mains electricity has a frequency of 50 Hertz, which means 50 times every single second the direction of the alternating potential changes. So what I can do is I can set this to 50 Hertz. And now you can see that both LEDs look illuminated. But that's because they are flashing so fast that our eyes cannot see them. Let's have a look at them in slow motion, and hopefully we will see that they complete one whole cycle in 0.02 seconds. Now, any appliance that we want to connect to the main supply, we've got to use a plug and a socket. And what you can see is that in the UK, we have 3 pins on this plug that fit inside the socket. Now, I'm about to take this plug apart. It's very important, if you're doing this in a science lab, that there's no way in which these plugs could be put in these sockets whilst we're taking them apart. Because if a mistake has occurred, we might be creating something very, very dangerous for our learners. Here is an issue. The other end of the wire might become live, even if it is correctly wired, and we plug it in here, with an amount of electricity that, if touched, would be fatal. So one thing you can do is press the circuit breaker and disconnect all of the sockets in the room, just to be sure. Also, instruct pupils not to plug it in And thirdly, you could do things such as taping up the other end of this, and also I have seen you can bend this earth pin so that it isn't possible to actually get it into a socket. Either way, be careful, but it's worth doing because you need to know what is inside this plug. At the very end of this video, you can watch me wiring a plug. It's fascinating, and it takes about 10 whole minutes. So I think we'll save it to the end of the video so you don't get bored and switch off right now. But if you really want to see that, it's at the end. Now with mains electricity, there are reasons why we send it as an alternating current. And we'll explain part of the reason here, though we will come back to it when we look at electromagnetism topic later. The main reason comes from this, ohmic heating. If I have a large direct current running through a wire, it starts to get hot. So what I'm going to do, I'm going to turn this on. I've got a wire here, nice fine wire, wrapped around a piece of glass so it's really obvious, plugging into this direct current at a high voltage. Now come on close, I want to show you what the thermal imaging camera can see. So to the naked eye, it doesn't look much different, but in the thermal imaging camera you can see all of that infrared radiation. It is giving off loads and loads of energy into the thermal energy store of the air around it. Now this is a terrible idea because what's happening, and you can see that that is going to 196 degrees, almost hot enough to start glowing, that this is just 12 volts. But what is happening is a very large current is flowing through this wire and loads of the energy is being wasted. If we were to try to send this electricity through the countryside, we would find that by the time it gets to our houses, most of it had been dissipated as heat, and very little would be left for our houses. So we've come up with a way of transporting the electricity without losing the energy as heat. So here we have a model which shows how electricity is sent long distance without losing too much of the energy as heat. So it starts off, and we'll move one by one to the thing that's the centre of the screen. Here we have our power supply. At the moment, it's generating an alternating current at the power station end. So you need to imagine that that thing there, that's the power station. And then the alternating current moves into this black device. This is a transformer. And now we'll do more about the transformers in the electromagnetism topic. But what that transformer does is it makes the electricity that follows it very high voltage and very low current. The wires then pass over these pylons here, these two wooden structures, carrying pylons like you see with the pylons out in the fields, out and around. The electricity then goes into another transformer. You see that black object just there. That turns it from high voltage and low current back into a higher current and a lower voltage, which, if we turn it on, should pass electricity to the light bulb at the other end, which you can see has illuminated. But an interesting thing is if I turn this to direct current, which it is now, the light bulb has not illuminated because all of the wire between here and there has not been able to carry the energy without losing it as heat, and it was also not the right kind of current to go through the transformers. So though we will talk about this in more detail later, you need to be convinced that alternating current is necessary for the transportation of this electrical energy over large distances using these devices known as transformers. So there we have it. Alternating current, direct current. Alternating current, direct current. So let us now have a look at the plug. It's really important when we're doing a plug that we have these pieces of kit. So a screwdriver, wire strippers. This is an automatic wire stripper. and a pair of pliers, though I have got a sharp cutting edge just here that I could use instead of pliers if needed. So I need to release, just here, this centre screw, which is quite tight in this one, and this is going to enable me to have a look inside. So let me get it out completely. And we can take a look at what is inside. So it should release from the case. And there we go. So you can see just here that the wire comes in from the outside. It's held just here. And we have the live wire, this brown wire, coming to this top point, which enables electricity to go through the fuse, before coming out of the pin connected to the live wire, this right hand pin. The neutral wire, this blue one, goes round to the other pin, which is visible just here. A green and yellow striped wire is an earth wire to protect the circuit if something goes wrong. Here, the neutral wire should normally stay at 0 volts, with the brown live wire oscillating between positive, well, it can be even more than 230 volts, but on average about 230 volts, positive and then negative, then positive and then negative. This is the wire that needs to be cut off in the event of an emergency. And so that is why the fuse is connected to that. Now, one of the things that's a good exercise to go through is rewiring the plug. So how to do that? First of all, we must undo these two screws here that is holding the wire in place. Once they are completely unscrewed, we should find the little wire guard is ready to come off. So just take it all the way to the edge. Now you can see it has come off, and the two screws that were holding it on are also off. We must also release these 3 screws just here. They're a little bit fiddly, and they're a little bit hard, so we'll just have to make sure we're accurate with our screwdriver. And there we go, releasing the live wire, releasing the earth wire, and releasing the neutral wire. All 3. And now what we should find is, if we've released them enough, these wires should all pop out. A bit of leverage from the lever there, just to make sure that they all pop out like this. Still held. So a little bit more. There we go, that one's out. And finally, the final one, the live wire. Let's fish that one out as well. So there we go. We have a complete separation of our electrical cable from our plug. You could go one step further and ask people to take the fuse out, and this one is going to release sideways, so you can see it pops out just like this. Try and keeping it all together so that you can see. There is the fuse out. Also in this plug, all of the pins also pop out. So that is the complete disassembly of the plug. And now it is the challenge of getting it all back together again. Now, a really good thing to do to start the process is to completely start again with the wire. So what I'm going to do is I'm going to snip off the wire like that, and say, well, that bit's got to be thrown away, and we're going to start again from scratch. Now, looking at how much cable was present on the green wire shows me that I need to strip the new piece of wire down here. So the very first thing I'm going to do is, it makes it easier to strip the wire if I slightly stress the cable at the point where I'm going to strip it. And I'm going to do that by half squeezing the wire strippers at that spot. Then I'm going to place it in the jaws, and hopefully it should break it at that point. And I might have to put it in a couple of times. You can see I'm getting good. I might have to pull it a little bit, but I'm basically getting a good separation of the outer layer of insulation. I'm just going to pull it off. It's nearly there, I just can't get the last bit to come off. There we go. Now one thing to now look at is to check that stressing the insulation and pulling it has not broken any of these cables here. These ones all need to be intact, their insulation needs to not be affected. What we can also see is the green wire, the longest wire, has been stripped so that the top bit of it, just here, has been stripped like that. The other two wires, if we look at this, the blue wire and the green wire are not quite as long as the green wire, so we need to actually cut them down a fraction. So we'll cut them and then we'll strip them slightly lower down. Now if you find you have not got enough wire, you can always pull it back, pull the insulation back a little bit. And normally you can just grab it and pull it back and snip off the excess that you do not want. So I'm going to snip that off, and then I'm going to expose both of these, that one, and I'm going to expose this one like that. So now I have my 3 wires exposed and ready to go. So the next stage, I've got to put the plug back together. I'm going to put the earth pin in, and that's the only one that looks like that. Now I've got 2 cables here. The one with the small holder for the fuse is the live pin. There's the other end of that, which goes in just there, and then the neutral pin. Now this is the bit that's quite tricky to do and people really struggle with it. I recommend at this stage that you bring the actual pins all the way out without falling out. And what I'm going to do is I'm going to put in, let's go with the earth wire. A small twist, just to make sure that all of the little tiny wires are together, and then I'm going to poke it in until I can just see through the little tiny gap on the side that it's poking through. Then, holding it still, I'm going to wind this up until it has got a firm grip, and a small pull just confirms that it is. The next one I'm going to do today is the neutral wire, which I'm going to place in just here. Now what you might find is that the green wire has to bend in order for you to get that wire in place. So let's get it in, and what I ideally want is all of the threads to go into that terminal. I want no loose threads inside my plug, and you can see it's completely clean there. I'm going to then tighten that one up there. Tighten it up. Now the final stage is we must make sure that these cables are twisted around the little tiny section there where the actual main plug screw, so it doesn't foul that area there, so you can actually get the plug back together. Some people find when they do this is that they foul that and then everything looks right, but they just can't get it to go, the case to go back on. Now the live wire is a bit tricky. We push it into there, and that is perfect. Screw it up, and we're good to go. All of these just need to be nipped up, and we should find with a pull it doesn't come out. We can put the fuse back in, it doesn't matter which direction we put it in. Then we put the cable tidy back on, and to start with it's a bit awkward, so sometimes it's about just putting your thumb on and giving it a little screw like this. Then get the other one, and like this. Just line it up whilst looking at the top side is probably the better way of doing it. Get that cable right in the middle. It is slightly fiddly, but what we find is that with a little bit of practice it can be done. And it is so much better to have a go at actually doing this than to just see a diagram. A diagram might prepare you for the exam, but actually wiring the plug will prepare you for life. So we give this a nice screw up, like this, till it is holding that cable nice and firmly. Nothing has moved, everything is in place. We should now be able to put it back in the case, and we should find that it sits snugly and that we can do that screw back up. Well, that is how you wire a plug.